becomes open because there's no other reason to be open. There's no current pushing this diode to become on. But if we have some energy stored in the inductor in the state on, then when you open the switch, then this initial current inside the inductor, it's going to push this diode to conduct. So these are the two states that we have for the buck converter. Either our circuit is going to look like this, is going to behave like this when the diode is open and the switch is closed, or the switch is open and the diode is closed. Again, later on we will see that in the second state we might get to a point, because this current eventually is going to decrease. If it decreases to a point that the current flowing through the inductor becomes 0, then the diode will become open. But like in this course, we only analyze the circuit assuming that we always have current flowing through the inductor. So let's see how our inductor voltage and current would look like. So this is VO, let's call it VO, this is VO. So first assumption that we have is that we analyze the circuit in the steady state mode. The second assumption, which is kind of implicit, is that we assume that our capacitor is large enough to maintain the voltage here, and the output voltage doesn't change that much, right? You guys remember that the time constant of an RC circuit is R times C. So if C is very big, it means that the rate of change of the voltage, it's going to be very slow, right? So if C is large enough, over one period, the output voltage is not going to change that much. So this is another assumption that we have. Now let's look at what the inductor voltage look like. So the inductor voltage is basically the voltage across the inductor, right? So plus minus VL, right? When the switch is on, the voltage across the inductor is VI at this node and VO at this node, right? And this is a buck converter or step-down converter, so VI is bigger than VO. We're going to see why that's the case, but right now, so VL, it's going to be VI minus VO, right? There's going to be small changes in VO, so I'm just going to write average VO, right? We said that C is large enough so that output voltage doesn't change that much, but it still like has some small changes. I'm just going to write this on the average. Most of the analysis that we do here is over one period, so this is the output voltage average over one period. When the switch is open, the voltage across the inductor, you can see that at this point this is 0, at this point this is VO, right? So 0 minus VO. So then it becomes negative VO. Again, I'm going to write average. So this is what we have for the voltage across the inductor, right? And this would continue again. If we just like keep having this switch on and off with the duty cycle of D with the period of T, this would just continue. So like this positive voltage, negative voltage, and so on. Now let's look at the current that flows through the inductor. So the current that flows through the inductor, so VL is L dIL over dt, right? Or I can also write dIL over dt is equal to 1 over L VL. If VL is constant, it means that IL, it's gonna either increase or decrease based on the sign of VL linearly with the slope of 1 over L times VL, right? So assuming that we have an initial current in the beginning of the period, this is our period, this is like 0, this is period, this is dt. So because we have a positive voltage across the inductor in the first state, this is state 1 when the switch is on, this is state 2 when the switch is off, right? We have a positive voltage across the across the inductor, excuse me, and it's constant, so it means that the current that flows through the inductor, it's going to increase with the slope of what? With this slope, right? So the slope of this line, it's going to be 1 over L times VL, which is VI minus VO, right? And as soon as we open the switch, the voltage across the inductor now is a negative number and it's equal to VO. So now the current, it's gonna decrease again linearly, this time with the slope of, so slope of, just like do this, it's a negative slope. It's going to be 1 over L negative of VO. So this is the slope of the second line. Okay, let me just like erase this part here now, just to do this. So this is what we have for the voltage that goes through the voltage across the inductor and the current that flows through the inductor. And again, this would continue, right? So the analysis that we do here is for, so this is the third assumption that we have, is that we always assume that there is some current going through the inductor. The current never becomes 0. This is called continuous conduction mode, or CCM. Okay, so this is what we have, right? So all the analysis that we're going to do right now, it's going to be for CCM. Now here, we assume that we're in the steady state, AC steady state, or average steady state. So what does that tell us? It tells us that the average of the voltage across the inductor has to be 0. So this area has to be exactly equal